and welcome back to another episode of Master's Class. So, we're going to be talking about the scientific revolution and why it matters. Well, the scientific revolution matters largely because it's going to lead to the most sweeping changes, not just through Europe, but throughout the world in the 16th and 17th centuries when it sparks off. It starts off technically earlier than that, but it doesn't become scientific until about the 1700s. We're going to talk about why that is as well. But the revolution, the scientific revolution, kind of comes in the aftermath of the Renaissance, an artistic revolution, and it coincides with the Enlightenment, a more philosophical revolution, the way people change their thought process, how they see the world around them, how they wish to be governed. Political philosophy certainly is influenced. So the two often go hand in hand. So we're going to see a lot of scientific, technological changes, advancements in mathematics, and the application to practical everyday life as well. And as a result of this sort of scientific revolution, we're going to see the way Europeans look at themselves, how they perceive the world around them. We're going to see a drastic, sweeping change. So let's get into what that drastic, sweeping change might actually look like, hey? So it kind of starts with natural philosophers. All right, so in the Middle Ages, we have these medieval scientists known as natural philosophers, but they don't actually observe the natural world around them the way you might think. Instead, they typically rely on the authorities of, scholars from antiquity, ancient authorities, Greek philosophers like Aristotle, who is no doubt a great influence on some of the figures we're going to be talking about for the scientific revolution, some of the observations that he's made about the world around him. He certainly made observations about the natural world around him. Early concepts involving gravity, friction, inertia will be parceled out and then refined and given identifiable terminology. And they will be made into law, irrefutable law that the universe is commanded by. And that's going to be teased out by some of these, figures of the scientific revolution. So they follow individuals like Aristotle the same way that the natural philosophers of the medieval world did. But the only difference between the scientific revolutionaries that we're going to be talking about and these medieval scientists of these natural philosophers is that they actually challenge Aristotle. They question Aristotle. They question these natural philosophers. And we're going to see that during the 15th and then going really into the 16th century, a number of natural philosophers start to abandon the old ways. They start to challenge the works of the scholars of antiquity. And it's not that they just don't believe them, it's that they believe them up to a point, right? That's the whole point of science, is that we take what you've built your work on and then we poke holes into it and see, does it hold up? Is there anything that we need to acknowledge about, the truth, the veracity of your claims? Are they universally true? No matter where you go on this planet, does your philosophy, your hypothesis, your theory, can we make it a law? Is it guaranteed every time, irrefutable? Because if not, then we're going to keep challenging it. And that's where we start to see that really come in, that mentality in the 16th and 17th century. So from the medieval ages, we get into the Renaissance. And we have from the natural philosophers the emergence of the humanists, people who are more human-centric. They are concerned about the general well-being of human beings, not just philosophically speaking, but, medically speaking, technologically speaking, scientifically speaking. What can we do to advance the human cause? And a lot of humanists, as a result of the Islamic Golden Age, are able to gain re-access, mostly through the Crusades and the aftermath of the Crusades, and of course trade that comes afterwards, the works of the ancient Greeks and ancient Romans, as the languages and the works are preserved, particularly that of the ancient Greeks, by Islamic scholars. And then it makes its way back into European society, and mastering Greek and Latin now gives these Europeans access to the really newly rediscovered works of scholars like Archimedes and Plato, who was the teacher of Aristotle. And Archimedes was basically well, I mean, if you can think of a stereotypical mad scientist locked in a tower creating devices like doomsday devices, I mean, the guy was building a death ray through using light and mirrors in his tower. I mean, he was like the definition of a true mad scientist. But like any villainous, I'm not saying he's a villain, but any, stereotypical villainous, mad scientist, they're also geniuses. And their writings make it obvious that some of these ancient thinkers disagreed with their contemporary Aristotle and other accepted authorities of the Middle Ages. So thinking is going to change. It's going to be stimulated by new scientific activity. It's going to be based on technical problems, documenting these technical problems, and of course, careful observation and accurate measurements. I mean, we're going to start to see mathematics and science playing a stronger role in human society and human history. And innovations such as the telescope and the microscope make new scientific discoveries possible. These new instruments are going to be used to advance human cause. I mean, the ability of weighing out material and calculating before you load what is going to be shipped so that the ship can guaranteed hold what you're going to ship it is going to change business and human society forever. And of course, how do we even learn how to do these things? Well, once again, we thank Johann Gutenberg for that printing press. This is going to help spread these new ideas very quickly. So we're going to start to see massive advancements post-Renaissance, post-1400s, getting out of the 1500s, getting into the 16 and 1700s. We're going to see the rediscovery of ancient mathematicians, ancient scholars, ancient medical practitioners like Galen. And of course, we're going to see the key of mathematics proving invaluable to navigation, military science, geography. So we're just going to see advancements all around. And let's talk about some of those scientific breakthroughs and who's responsible as well. So we got a few big heavy hitters here when we talk about the advancements made in these sciences. So one of the things that we talk about is who are these individuals? What role do they play? And what are their innovations? What are their contributions? Well, we have a list you can see on the right-hand side here, which you can access, of some of these scholars, and we're going to be talking about them. These are the heavy hitters, these are the greats, but we're going to focus on astronomy and physics first, because that's like the first major breakthrough in the scientific revolution that's going to give way to how people are going to start looking at their world and their surroundings very differently. It's going to challenge religious notions, preconceived notions of their place in the world. And once you break that barrier, it almost feels like really anything is possible. And if anything is possible, then you can start to, free your mind and make breakthroughs in other fields. So it is worth noting that although these guys are astronomers, they're mathematicians, they're physicists, like Isaac Newton here, they're going to greatly advance just about every other field in regards to the scientific revolution. So we're going to talk about Nicholas Copernicus, Johannes Kepler, Galileo Galilei, and Isaac Newton. They all influence one another. So it kind of starts with Copernicus, and it's going to basically conclude with Isaac Newton. So let's kind of get into it here. So we have these breakthroughs. Breakthroughs in chemistry, breakthroughs in physics, breakthroughs in math. Astronomy. Just breakthroughs everywhere. This is a period of really profound intellectual stimulation. So, but to understand where these scientific revolutionaries are coming from, we have to look at those scholars of antiquity. So we're not just looking at Aristotle, who believes that the heavens are immutable and perfect. So the Catholic Church agrees with Aristotle on this, that they're immutable, they're perfect, they're celestial balls of light, the planets. And then we have Ptolemy, who lived in the 100s CE or AD. He's the greatest astronomer of antiquity, and he also kind of believes with Aristotle and the Christian view of the heavens. They both kind of believe, Ptolemy, Aristotle, and even the Catholic Church at this time, that like the planets are basically enshrined in they're like crystal spheres. They're smooth, they're perfect balls of light, they are unmoving, they are immutable, and beyond them there is heaven and therefore God. But Earth, and this is the most important part, Earth is the center of the universe. And that's the Ptolemaic system, or the geocentric, the Earth-centered based system. So whenever we have scholars in this era, up into the 1600s, they are operating off of a geocentric model. They believe that the Earth is the center of the universe. This is not correct, of course. This is wrong. We know this. But this is the prevailing notion, because it means, therefore, that God, all right, according to the Catholic Church, according to Aristotle, according to Ptolemy, God has therefore put mankind, and therefore man, at the center of the universe. So you can see how that idea, that notion, is very appealing to a religious system, certainly. Well, that's going to change. It's going to change. But there are some things that Ptolemy and Aristotle do get right, especially Ptolemy. So although the Earth being at the center of the universe is incorrect, although the heavenly bodies are pure orbs of light is also incorrect, although that they are supposed to be embedded in crystal-like transparent spheres that rotate about the Earth is also incorrect. He does set up a notion, he does set up a system of where the planets align with one another, which is going to greatly influence our knowledge of, the planets from the sun, where we switch to a heliocentric system, which we're going to get into in a moment. So Ptolemy believes the moon is embedded in the first sphere, Mercury in the second, Venus in the third, the sun in the fourth. We're a bit off here, but we do get this idea that there is clearly a structure and an order. It's just kind of out of whack. But a template has been laid for future astronomers to perfect. He believes that the rotation of the spheres makes these heavenly bodies rotate about the Earth and move in relation to one another. He's close, right? He's close. There's definitely going to be a rotation of spheres. They're going to move about in relation to the sun, and there is going to be somewhat of an attraction to one another by a gravity, but that's not really known yet. And Ptolemy kind of goes a bit off the rails here. The 10th planet, the 10th sphere, is the prime mover, and it's beyond this one that there is heaven where God resides. So God is at one end of the universe, and humans are at the center, thanks to where God puts them. So again, very cozy, very snug, kind of religiously bound rhetoric. Well, that's going to change. It's going to change with the coming of Copernicus, and certainly with Galileo. Kepler kind of straying the line in the middle here. But each one is going to start stripping away the idea of Aristotelian and of Ptolemaic systems, of the geocentric system of how we view the universe and our place in it. So Nicholas Copernicus, he's a Polish monk, and he kind of was obsessed with mathematics. He's going to land himself in a little bit of hot water. he is going to champion this heliocentric model, right? A sun-centered concept of the universe. So immediately, we're basically going to challenge the Ptolemaic system, right? We're going to get rid of that. So in 1543, on the revolutions of the heavenly spheres, he publishes this fairly controversial but very influential work. And we're going to start to see that, yes, the Earth is going to rotate around the sun, not the sun around the Earth. He's not correct in the fact that he believes that the sun is the center of the universe, of our particular solar system, certainly, as we're going to learn more and more about how big the universe actually is, infinite, and that galaxies are part of the universe, and a solar system is a part of a galaxy. But keep in mind, it's all a work in progress at this point. They're evolving our knowledge. We're getting closer. Things are still off with Copernicus here, but we're getting closer. Another big note from Copernicus, the apparent movement of the sun around Earth was caused by the rotation of Earth on its axis and its journey around the sun. All right, we're getting closer, right? We're getting closer. So now we've adopted a sun-centered, a heliocentric model of how the universe exists, and human beings are going to start to accept/challenge that. Can we prove it? Can we refute it? Well, Johannes Kepler, German mathematician, hits the scene. He's going to take the next step in destroying the Ptolemaic system. So he keeps very detailed astronomical data. He arrives at laws of planetary motion. He is a student of Copernicus. His observations confirm that the sun was the center of the universe. It wasn't. It's our solar system, but again, we're not quite certain of how big the universe is yet. Also adds new information. In his first law, Kepler shows that planets orbit around the sun, and their orbits are not circular. They are elliptical or egg-shaped. They have ellipses. The sun is toward the end of the ellipse rather than at the center. And this finding, known as Kepler's first law, contradicts the circular orbits and crystal-like spheres that were central to the Ptolemaic system. We're learning more and more now that the planets, these heavenly bodies, are not immutable. They move around. They move around in ways that we didn't think they moved around. So the heavens are not perfect. They don't just stand still. They move. So that's the first thing that's going to destroy the Ptolemaic system. It's kind of a challenge to the Catholic Church. But the big challenge comes from this guy, Galileo Galilei. An Italian mathematician, astronomer, general genius. He is going to refine a particular telescope that's going to give him a real clear view, the clearest view of these heavenly bodies. What are these planets made of? How do you explain motion in the universe? These are all things that he's curious about. So he's going to observe these planets, these heavenly spheres, and he finds remarkable discoveries. Mountains on Earth's moon, 4 moons revolving around Jupiter, sunspots. He finds damage. He finds movement. He finds that they are not smooth, crystal-like heavenly spheres at all. And so he's basically going to see, he's going to lay down to the rest that the heavenly bodies that had been seen as pure orbs of light simply weren't. They are composed of material substance. They're basically kind of like Earth. And so this destroys the Ptolemaic conception, and it lands him in real hot water with the Catholic Church. He is going to be challenged after he publishes his work in The Starry Messenger in 1610. This is a smash success. By the time the 30s and the 40s hit, his work is basically all but accepted throughout Europe, with the exception of Rome. the seat of the Catholic Church. Because again, this challenges the idea that God has placed mankind at the center of the universe. So after we get through with Copernicus here, we get into another scholar. Born in 1642. In fact, I believe that's the same year that Galileo Galilei dies. On the day he dies, Isaac Newton is born. How creepy is that? And he's going to take the work of Galileo Galilei, who ultimately Galileo Galilei had to, I mean, he destroyed the Ptolemaic system. He destroyed the fact that, God was no longer in a specific place, that the whole church concept of the universe has to be rethought of. It's changed. It's simply inaccurate. All the works of Copernicus, of Kepler, of Galileo Galilei have not been yet tied together, but that's going to happen with Isaac Newton. In England, after he is born, he is going to quickly become embedded in the world of mathematics. At a very young age, he becomes a professor of mathematics at Cambridge University, where he studied and attended. He paces around his desk like 16, 18 hours a day. He barely sleeps. He sleeps like maybe 3 or 4 hours a day, if that. He mumbles to himself while he's trying to unravel the mysteries of the cosmos and the universe around him as he's just pacing around his desk, wearing holes in the carpet. He's constantly pacing around his desk. His servant thinks he's a madman, but he is a genius. And he's going to publish perhaps the greatest work of all the scientific revolutionaries, his Principia de Mathematica, or simply his Mathematical Principles of Natural Philosophy. In the Principia, he is going to lay out in this one work the single, it's the single most influential advancement in our understanding of the universe. And it's going to lay out all these laws that we accept as true. We accept these as laws. Like these are not just hypotheses. These aren't just theories. They have been tested. They are therefore law. They are universally true. And so he lays out 3 laws regarding the motion that govern the cosmos. So he argues there is a universal law of gravitation. Finally, someone is able to capture what Copernicus has observed, what Galileo has observed, what Kepler has observed, even what Aristotle back in ancient Greece had kind of just naturally observed but couldn't quite articulate. An explanation for why the planetary bodies continue their elliptical orbits about the sun. Every object in the universe is attracted to every other object by a force called gravity. I mean, you have to understand how absolutely mind-blowing this would have been, and just how difficult it still is. That's the reason why he wrote it, in fact, is he didn't want anybody just to be able to understand, his work. He wanted the best, the brightest. Like, if you can understand this, then I know you're up to snuff. A little egotistical, perhaps, but he needed people to understand his work because he was also a follower of alchemy, a little bit more mischief, a little bit more mysticism. Alchemy they believed in things like turning base metals into gold. They believed in crafting a great work such as the Philosopher's Stone, where one may be granted everlasting life. So it's like pseudoscience, but he believed through advanced mathematics these are things people could figure out. But in order to figure that out, he needed people to understand his Principia. Because if you can understand the concepts I'm laying down in this bad boy, then maybe you can help me out with my alchemical projects. So, mad scientist, once again, but a genius, nonetheless. So, this one universal law about gravity mathematically proves and explains all motion in the universe. And from there, from gravity, we get friction, we get inertia, we get the idea of, a force that is put upon an object, moves that object, and is directly related to the force put on that object by that force. I mean, these are all things that we can measure. And it's really not going to be until Albert Einstein in the 20th century, into the 1900s, that we get a new concept about the universe. And the theory of relativity gives us a new picture of how the universe works. But I mean, Isaac Newton lays out that the universe is really one huge clockwork. It's a regulated, uniform machine. And he doesn't challenge the Catholic Church. He's very smart in this one. To him, where the Catholic Church accuses him, I'm sure, of, kind of abandoning God and trying to use science and math as a way to explain everything. He believed that it was, for his point of view, mankind's objective to understand math and science to prove God's existence and to better understand his divine clockwork, as he put it, basically the universe. So that's one way he kind of doesn't have to suffer the persecution or the excommunication that Galileo Galilei had to suffer. So he never had to redact, if you will. He never had to take back his work. But it's not just in astronomy we see these breakthroughs. We see them in medicine. We see them in chemistry. So we see a few individuals. Galen, a Greek physician, around the 100s CE, a lot like Ptolemy, right? So he is also going to advance the idea of human anatomy, but he relies predominantly on animals rather than humans for dissection. So, there are many instances in which Galen just doesn't quite have human anatomy worked out. And that's not going to be until, again, the 1600s, way later, where we have Andreas Vesalius and William Harvey. They're going to add tremendously to the understanding of human medicine and science at the University of Padua in Italy. They are going to dissect human bodies live and lecture while they do it, especially William Harvey. So they are talented artists, for one. They are able to write out and map out, human anatomy, the structure of the human body. They can show where the organs are. They can show the structure of the human body. They are able to articulate the beginning point of the circulation of blood. They are able to work out the system of veins and arteries that makes up a complete circuit through the body. This is huge for understanding of medicine. In chemistry, we have two big names. We have Blaise Pascal, and we have Sir Robert Boyle, one Frenchman, one Englishman. They both do the same thing, essentially. They work a lot with pressure and how certain, elements behave under pressure. Pascal focused on liquids. He applies this principle to the development of tools such as the syringe and the hydraulic press. He measures and gauges how water versus blood versus red wine operate under pressure. And we have Robert Boyle, who, much like Pascal, works with pressure but with gases. His work on the properties of gases leads to Boyle's law, which states that the volume of a gas varies with the pressure exerted on it, not too dissimilar from Pascal's law. And we have the contributions of women as well. So women typically are not allowed into the university system at this time, in European society particularly, to participate equally to men. And so a lot of women who are aspiring astronomers or chemists, mathematicians, scientists, and any philosophers, they often post their works and publish them under pseudonyms. They do them under fake names, handles, if you will. They publish anonymously. They don't publish under their real name for fear of, controversy, criticism, and having their works completely discounted, just because they're women. But we're going to see a little pushback on that. So we have Margaret Cavendish, she's a philosopher, and we have Maria Winkelmann, she's an astronomer. They're both going to advance science through their work. Cavendish is a bit more outspoken than Winkelmann, I would say. She comes from an aristocratic family. She's well-read. She's had the proper upbringing of what is to be expected from, a woman from an aristocratic family. You have knowledge of music, dancing. You can certainly read and write, needlework. But although she's not formally educated in the sciences, she wrote heavily on scientific matters, including observations upon experimental philosophy. So she's bridging the gap between what it is to be a natural philosopher and a scientist at this stage. So she is critical, and this is something that I think we're facing right now with our epidemic. That we use science to become masters of nature, right? To overcome, really to defeat death. We want to live longer, and we are. We are living longer lives, human beings. We want to live healthier, longer lives. We want to defeat death. We want to overcome. We are part of nature, but what we want to do is to become a part from nature. We want to remove ourselves from the cycle. And what she has to say in her observations upon experimental philosophy regarding this matter is that, quote, "We have no power at all over natural causes and effects, for man is but a small part. His powers are but particular actions of nature, and he cannot have a supreme and absolute power," end quote. So she publishes under her own name. This is against what is commonly done for female authors at this time. Her contributions of philosophy are widely recognized today, very influential amongst the intellectuals of later generations, but not so much of her own time, as scholars of her time did not really take her works very seriously. Certainly not like an Isaac Newton, certainly. In Germany, we have Maria Winkelmann. She grew up, like some women do, where their fathers, their brothers, their husbands were, astronomers, and they learned from them. She grew up working in a family of astronomers in their observatories. Her father and her brothers kind of trained her. She would eventually get married to Gottfried Kirch. He was Prussia's foremost astronomer, and she becomes his assistant and wife. And she greatly, advances the field as a result. She is one of many women who make up this field. Between 1650 and 1714, about 14% of all German astronomers are women, which is pretty high for that era, especially considering that these women are not formally universally trained, is what makes it the most impressive. So after her husband dies, she discovers a comet. She makes her own contributions to the discoveries of comets and moving bodies and planetary motion. And her husband dies, and she doesn't want to stop, so she wants to become an assistant astronomer at Berlin Academy. And she's quite highly qualified, but as a woman with no university degree, she's denied the post. And members of the Berlin Academy fear they would set a bad example by hiring a woman. And it shows that even during the scientific revolution, for as much challenge there is to the way we view the world and understanding of the world and nature, there are still old holdouts and preconceived notions that people hold to. It's much different today, obviously. I mean, over half the engineers that work on the Large Hadron Collider are in fact women. So it always takes somebody like a Margaret Cavendish, a Maria Winkelmann, a Caroline Herschel, if you will, to challenge preconceived notions, the status quo, and to advance the world and how we see it. And speaking of challenging the world and how we see it, this guy, I have my college students read René Descartes and Cartesian Doubt, and it warps their brains. I'm not going to lie. It's mind-bending stuff. In fact, if we're familiar at all with the movie franchise The Matrix, the very concept of The Matrix comes from the inner workings of Cartesian Doubt, the works of René Descartes. What do you really know about the world around you? Because your senses, your observations of the world around you, they can absolutely fail you. They can be false. They don't have to be true. They can mislead you. He invented a thought experiment. And once again, this will sound like The Matrix to you. So René Descartes invented a thought experiment where he postulated that pretend and believe that there was a scientist, a mad scientist working in a lab, and he had created some sort of gas that he unleashed upon the world, chemical weapon, that put everyone to sleep. Everyone is asleep, right? They're kind of under this scientist's control. Now, and while you're asleep, he makes you believe that you occupy a world in which he is in control. Is that real? Would that existence of yours be real? And so that's where things kind of get a little crazy, right? Because what is real now? Your existence has certainly changed, but you are still a physical being on Earth. You're just not viewing the Earth and the world that you actually, you actually exist in the way you should. You're kind of being controlled by this mad scientist in his experiment. So he really does challenge how we see the world and really how these scientific revolutionaries. So he's part, we often put him because of his advanced mathematics, but he's mostly a philosopher as part of the scientific revolution. We certainly should, but he's also kind of the guy who bridges the gap between the scientific revolution and the Enlightenment, which we'll talk more about tomorrow. So his philosophy largely dominates Western philosophy until the 20th century. He casts doubt and uncertainty on everything, and therefore we must find a way to make sense of the world around us. And this is something that he is going to point out in his Discourse on Method, written in 1637. He's going to cast doubt. And he is highly influential on Isaac Newton, who reads his work and everybody else's that came before him to come to his own conclusions. So he says, let's set aside all that we have learned and begin anew. One fact to him seems beyond doubt. His own existence, right? So when he goes into this thought experiment of being trapped by this mad scientist in this sort of dreamlike state where he is controlled, and the world that's being presented to him is a false world because his senses are betraying him. What does he know is true? Well, he knows that he exists because he thinks. And so therefore we can put importance on one's own mind. We can accept that the things that we are able to reason may be true. So his first concept, his first principle that surrounds his entire philosophy is ergo cogito sum. I think, therefore I am. So Descartes uses his reason to arrive at a second principle. The mind cannot be doubted, but the body and the material world can, and the two must be radically different. So from this idea came the principle of the separation of mind and matter, and of mind and body. And this is going to lead to the concept that scientists today will use. He is the father of what is modern rationalism. Basically, the system is based on the belief that reason is the chief source of knowledge. We must be guided by rational thought. Knowledge comes from rationalism, our ability to reason, to determine what is true. And from this, we get Francis Bacon, an English monk, chemist, mathematician, scholar, who is going to, in large, be responsible for the scientific method, kind of the father of the scientific method. So rationalism sets up the scientific method, a systematic procedure for collecting and analyzing evidence. So the method is crucial for the evolution of science in the modern world. So Francis Bacon, a philosopher with few actual scientific credentials, believes that scientists should not rely on the ideas of ancient authorities. Instead, what they should do is learn about nature using inductive reasoning, basically proceeding from the particular to the general. And we can even find this chart that shows the process of the scientific method. So we begin with inductive reasoning, right? We are making observations from some natural event, and from there we form a hypothesis or a possible explanation of the observed event, and then we can go into empiricism. Knowledge achieved through observation, right? This is how we are going to get to perform experiments to test our hypothesis. So empiricism coupled with experimentation and inductive reasoning, what we observe from an event around the world around us, leads to a greater understanding of the natural world. So we start very particularly, and then we can maybe make a very broad general statement that is universally true, that might even become not just a theory, but a law, such as found in Newtonian physics. So before beginning this reasoning, scientists try to free their minds of opinions that might distort the truth. They start with detailed facts and proceed toward general principles. From observing natural events, scientists propose a hypothesis, bam, possible explanations for these events. They then get into systematic observations. That leads to experimentation. We test a hypothesis. We see what is true and what is not true. We analyze and we draw conclusions from the results. Do those results support the hypothesis? If yes, publish results for other scientists to review. If no, revise the hypothesis based on the results, and repeat until the hypothesis is strongly supported by those results. Francis Bacon right there. So he states, the true and lawful goal of the sciences is none other than this, that human life be endowed with new discoveries and powers, right? And that's the truth of science, isn't it? Margaret Cavendish says that we constantly struggle, but we will never obtain supreme power. But Francis Bacon basically says, well, with these new discoveries, we're endowed with powers. Maybe they're not supreme powers, but they are powers. We essentially level up as Homo sapiens. Because we see these advancements from the benefits of science in agriculture and trade, not just in science itself or mathematics. He said, quote, I am laboring to lay the foundation not of any sect or doctrine, but of human utility and power. Human power could be used to conquer nature in action. Maybe not supremely, but we can overcome some aspects of nature that we have been held victim to, and who knows, perhaps even one day we remove ourselves from nature itself and we do the ultimate thing. We defeat death. But that is a lesson for another time. Thank you very much, everybody. That'll do it for our live lecture here. And this episode of MasterClass on the Scientific Revolution. Stay tuned for the Enlightenment next time.